So there were a couple of people where things didn't work because in their launcher some instructions were missing. So the launcher is what is stored under your home .local shared Jupyter kernels my environment kernel. That's the subdirectory. And the launcher is this particular file. And let me show you my file. And it's this. Those are for Ascent to avoid warning messages. Okay? But then the module loads are right here. What is useful to me, FFmpeg, Ascent. Ascent itself loads the conduit module. So you should not have to load conduit. Visit is what I wanted to have to demonstrate that I can read HDF5 blueprint files with visit. Matplotlib is what I have here, module load matplotlib. This line is also for visit because currently it's missing in the installation of visit on PitsDate. So those 4 lines, well, were missing for some of you, and it's for the following reason. This is a clone of my repo, and perhaps I forgot to tell you, or perhaps whatever. You should do a git pull to get the most recent stuff. Okay? Yeah, in fact, do a git pull. You will get the latest and greatest copy, okay, the latest only, copy of my PDF slides. Fine. More important, the instructions for PitsDate, and it tells you specifically what I've done to build everything. I've done this and that and that. I created my environment, and then I installed IPyKernel, Wheel, Cinema Science, and I created my environment kernel. So up to here, I think everybody has that. I've seen one person where those instructions were missing here. So what you should do, and it's better if you cut and paste without the line breaks. Be careful here. I've made the screen big for you to see. Those instructions, SED, they add to the content of home.local shared Jupyter kernels, the launcher, they add the instructions required. Okay? All right, now, one other question which was asked to me before the break. If I go to examples, for example, Lulesh, this is what you have in the repo. I'm here in the clone of the repo. Well, I have instructions on how to compile and run on PitsDate, both for Ascent and for Catalyst. So, for example, if I look at those instructions here, you would see that once the code has been instrumented, you need to compile and link with the Ascent library installed at CSCS. This is what I do. A module load day in GPU, CMake, Ascent, create HDF5 parallel. I create a build directory, and this is my CMake command line, CMake -d in-situ Ascent. You have to specify the HDF5 include div because for some reason it doesn't find it. That's CMake. And then ... That's the source code, the place where the source code is. And then you make. How do you run with Ascent? You submit a batch job called, in this case, run lulus ascent sh. Let's look at the content of this file. This is demo stuff, so it's pretty small. 10 minutes of runtime, 1 node, 8 tasks per node, module load int, GPU Ascent. And then I can't read. Oh, it's because I have my reading glasses. I make a directory under the scratch partition. I copy my executable to the place. And to enable a custom scene description, I copy my Ascent action YAML file and the other one, because this one needs this one, I copy them to my running directory. I push to this I change directory here, and then I just simply run with srun my executable. And that executable will read the Ascent action YAML and this file. Let's look at the content of those files. More Ascent YAML. It will add a trigger. This is the content of my pipeline. Add a trigger. This is something we have not seen yet, so it's very good. So yet another example. Trigger, first trigger, params, the condition is whenever the iteration step is modulo 100, execute this. What does it mean? It means that my visualization script will be executed every 100 iteration. Okay. So this is an example where we combine together. This could have been written all in one single action file, but here, to separate things cleanly, I've put the trigger separately. On each iteration, modulo 100, execute this, and let's look at the content of this. I forgot what I put there. I put a pipeline. I want to visualize the velocity, but I first have to compute the velocity magnitude. So actually, that's my first pipeline. I wonder if the definition of magnitude is missing here. Type. Yeah, I don't see the definition. It's probably missing somewhere. And then I have a scene and my pseudo color of velocity. No, actually, no, nothing is missing. I'm sorry, but this is actually this is a predefined operation. I was confused between velocity and vector magnitude. Vector magnitude is a predefined operation in the Ascent API. So I have defined a pipeline where I compute the vector magnitude of velocity. With this pipeline, I call it velocity magnitude, and then I can color with it. Let's look at the other example, Jacobi testing. Same thing, pretty much. Load my Dane GPU module, my Ascent, my matplotlib, and then I can run all 3 copies. I told you there were multiple copies. They're Jacobi, In-situ, serial. It's called In-situ just because the file name is the same, but this one does not have any In-situ coupling. It only uses matplotlib. This is the second version where the Ascent code is added. And this is the parallel version where I use Python in parallel with all the tasks available to run the code here without Ascent and with Ascent. There. There was one more question, perhaps you, Sri, had asked me before the coffee break, and I said I would answer it.
That was this how to use Ascent while the code is running.
The microphone, yeah. The question is how to use Ascent. How do you actually, while the simulation is running, producing the visualization outputs, how do you see that things are actually running? Well, the first trivial thing is you change directory to your Scratch file system. You can see here all the different outputs that are indexed by time step, all the different images and so forth. But there's also a Jupyter Lab interface where you can connect to your simulation. That I have not installed yet at CSCS. I've tried, but I didn't manage it right away. So it's work in progress. For the installation part, it's a product that is documented in the Ascent documentation page, so I know it works already. Cyrus Harrison at Lawrence Livermore has told me he would help me figure out the details. So we can connect live via a Jupyter notebook to the simulation to see the different state of your simulation.
Ascent doesn't have a GUI like ParaView?
No. ParaView has multiple, this is my next slide. ParaView has multiple forms. One of them is the desktop application with a graphical user interface, etc. Ascent does not have that. All right, so that's actually my next slide. Before starting to talk about Catalyst, let's talk about ParaView itself. Those are slides that Francois has prepared for me. He will present those in Hamburg next week, but I can summarize that very, very well. Again, ParaView, as I insisted earlier, is open source, so really, really great for us here at the Computing Center. Multi-platform. It works with all the different operating systems I am usual to see. And it does analysis and visualization. This is what I like. Just like Ascent, just like Visit, it's not just about making pictures. It's also about doing analysis. For example, there's one of the notebook we did not have time to go through, but you have it. It's notebook number 7, if I recall. It shows you how to do analysis with a Python script. Now, with Ascent. But that analysis is based on some standard NumPy and families of analysis toolkit. And what you pass to that is a conduit mesh. So it shows you how to actually get data from your conduit mesh description, pass that to your standard Python analysis modules. All right. So both Ascent, which derives from the earlier work of Visit, and ParaView, they have demonstrated performance over gigascales and terascales of data. Here it's hard to say. Those are actually old pictures. Trust me, the 1 billion and half billion cells, that's not peanuts, but I mean, I do 10 to hundreds of giga cells today very comfortably. Those are old pictures, but fine. Francois did a favor to me. He put pictures that actually John, remember John? When we did the Pelton turbine, we did those pictures years ago, 10 or more years ago. ParaView, just like Ascent, has this parallel rendering infrastructure such that you can have independent MPI tasks doing a partial rendering of their local data, and then the final data is actually merged here with ParaView with a library called ICE-T, which does what we call image compositing. So this is all an infrastructure that we will use when we do in-situ. Of course, the distributed processing is also there. It seems like I'm talking about the same thing as in the previous slide. But this is about rendering, parallel rendering. This is about parallel processing. And it can be in ParaView that you have a different server to do parallel processing, and then you pass that data to a subsystem with a different number of tasks which does parallel rendering. Francois tells me that he has several customers that do that. At CSCS, I've never tried to differentiate between the parallel image rendering subsystem and the parallel processing subsystem. It's all the same. So I have the same number of tasks. This is what I'm saying. In other words, the data server and render server at CSCS are merged into a single parallel engine. There. The client has a display, and that's nice, so we can actually connect a desktop application to the parallel server. Okay? There. So ParaView can run in multiple ways. In batch mode, this is what I do a lot of the time, with a client connecting to a server at a remote location. I've done it across the world on different servers. It works very well. It has optimizations for image transfer, color encoding, color compression, etc. So it's very efficient indeed. You can also have a ParaView web interface. Now, the in-situ part of the analysis is done with Catalyst. ParaView Catalyst, as I had alluded to earlier, is actually one implementation of the Catalyst API. Catalyst is one definition of a process to do in-situ coupling. ParaView Catalyst is an implementation of it, and the principle should be pretty obvious by now because it's almost 4 o'clock. Instead of saving data to disk and then reading the data back over here with ParaView, the simulation with the help of Catalyst and ParaView will do intermediate data processing and filtering and rendering and save only the smaller part of the simulation to disk. Some examples of savings in storage here with this helicopter blade dataset. We passed from an output of a full dataset per time step of 450 megabytes to a few megabytes of geometry and images. Other example here from a live simulation done at Électricité de France in Paris. This is code Saturn, which has been over here, which has been instrumented to run with Catalyst. So, yes, there was one comment from a participant before the coffee break. He was asking me about the positioning the camera. And of course, we do not know a priori where to put the camera in an in-situ setting. So the recommendation is to try with a small size data set, because most often we will run simulation at different scales, but if I can say, the geography or the setting of things in space is pretty much the same. So you can prototype your camera movement with a small data set. There are more examples. So Catalyst is pretty mature. In fact, those are examples from a few years ago already. For example, the instrumentation of the code FASTA at UC Boulder. And in fact, Catalyst is more than 10 years old. It started with the co-processing effort at Kitware, which Andy Bauer had initiated with his colleagues, and then it went through different versions of the code. Zero copy is what we call shallow copy also. This was a crucial step in the implementation. Particle path is an example of a particular algorithm that has been made custom just because of I had said earlier, when you want to do particle tracing in time, you need access to time steps in the past, which you usually don't have in an in-situ setting. So there is an example of an algorithm that supports this. Around the years 2017-18, there was the script generator such that the ParaView desktop GUI application would assist you in writing the Python script necessary for the in-situ execution. And pretty much at this stage of the pipeline here, Catalyst version 2 and the scripts versions 2 appeared. And let's be frank, I've never liked the previous version of Catalyst, so I wasn't very excited about sharing it, teaching it, and this is much better. This is much cleaner now with Catalyst version 2, so I'm really excited to talk about it and deploy it at CSCS. Steering is in a development stage. François has demonstrated to me. It's still a little bit, how would you say? Gotta be careful here, not to offend anybody. It's work in progress. Let's put it that way. I will not demonstrate it today. So Catalyst 2, the goals were to make it much more simpler. I had told you earlier that in the previous version, you had to know the internal data structures and types of the VTK object to be able to do a coupling. This is all gone now. Today we use Conduit. Conduit is an intuitive, easy to use interface to describe your data, and ParaView under the hood maps those descriptions into the real VTK object. But this is completely transparent to you. You don't see those VTK objects anymore. Easy to build. It is easy to build because you compile conduit on the side, and then you add that to the Catalyst compilation. Easy to deploy and to maintain. This is also very important, and this is done very well because there's actually two different things. There's a so-called stub library, which acts as a template with the 5 calls which make up the Catalyst API. Catalyst initialize, Catalyst execute, Catalyst close, and I forgot the other two, but initialize, execute, close, about, maybe. I think they're listed here. Which means that you can instrument your code without ParaView, but using the stub implementation of Catalyst. I compiled that yesterday on pitch day. It was a couple of minutes of git clone, cmake, make, bam, it was done. And at runtime, you actually can say, hey, at this point I'm ready, I want to use the ParaView implementation of the Catalyst API. So this is all done. We've seen conduit, so this is now an acquired skill. We will go directly from the simulation with the Catalyst adapter to ParaView. There are the 5 calls I wanted. Yeah, one of them was about, I said it right. The last one I was missing is Catalyst result. So those are the 5 calls which are both implemented in the, basically implemented as a no-op operation in the stub implementation, and which are implemented fully in the ParaView port. Catalyst has its own development site and documentation, so I refer you to that pointer for details, but this is pretty actually small, pretty quick to go through. Catalyst 2 is inspired by the MPI and Pitch ABI compatibility initiative. If you're familiar with that, this is an effort by different vendors to make sure people could switch between MPI implementations in a binary compatible way. So this is exactly the same way Catalyst uses to do its switch of Catalyst implementation. Basically, this is done with specifying at runtime an implementation path and an implementation name. At this point, I only know one version of an implementation of Catalyst, and that's the ParaView implementation. So I can use that with the ParaView name. There, I've said basically all. The difference between the Catalyst stub implementation with no external dependency, and then the Catalyst ParaView, which ParaView does. Steering, this is the 5th call in the API. This is what allows us, for example, here's a screenshot of the graphical user interface. It allows us to pass some a very small subset of parameters, numerical values, back to the simulation via this particular API call. But I haven't exercised that, frankly, so I will not give you more details on it. All right. In the roadmap, there is also the support for field data. In the ParaView vocabulary, there is what we call the point data, which are the data scalar field, vector field, tensor field, etc., associated with vertices. There are the so-called cell data, and then there is the third category called the field data, which are data available globally for the mesh. For example, just the names, annotations, which are global to the whole mesh. Well, this is not this is in the process of being supported also via the Catalyst interface, such that we can use those global variables, field data, also in the calculations of results via Catalyst. And then in transit, based on ADIOS, this is also work in progress. The same thing for Ascent. It's still listed as a work in progress in the Ascent documentation. This is why I give you appointment next year in this room to go through all the in-transit support. All right, so now to the specifics with ParaView. We've learned how to instrument our code, how to write the mesh definition. This is pure conduit. Now you are all experts because it's pretty simple. How do we compile with ParaView Catalyst? There are examples. This is the one I had here earlier. I had Ascent and I also have Catalyst, perhaps. How do we compile? On PitsDane, for example, we load Dane GPU, we load CMake, we load ParaView, and then we compile with a flag. This flag is actually specific to the Lulesh implementation. You can call that flag anything. Just tell it that you use Catalyst, and then you pass the Catalyst dir directory as an option. And this is the path where CMake will find the libraries related to Catalyst. At CSCS, because we use EasyBuild, this will be hosted under the variable EasyBuild root ParaView lib CMake ParaView 5.10 Catalyst. And then we pass a port. We tell CMake to use CC as the compiler on PitsDane, and we make. And that's all we do. How do we run it? Here's an example: sbatch run lulesh.sh. We will look at the content of this file in a second. We have to associate, okay, the difference between Ascent and Catalyst. No, first of all, let me backtrack. The common denominator between Ascent and Catalyst is the conduit mesh definition. On top of this, Ascent adds the scene description, which is also done with conduit node. Okay, ParaView does not have that scene description. ParaView reuses the mesh definition and adds to this a pure Python script definition, and we will see how this is generated. So to run a ParaView a Catalyst instrumented simulation, we have to have a Python script. So in this example, this is a script.py, and it will use extractors, and I will define what those things are. The first extractor in this example saves data to disk at a frequency given by this parameter. We will see that, what it is. And here you can define any frequency every time step, every 10, every 100, every whatever. ParaView will do it. You have the so-called image extractor, which will do a rendering of your scenes at a given frequency. and that's it. So let's look at the detail of one Lulesh catalyst. Yes. This is all in the repo, so you can all exercise those. And for those of you who have accounts at CSCS, I think it's most of you, next week you switch back to your other account, all of those things should work as published. To run things, I load date, I load ParaView. There's a bit more stuff here which is commented out because I was trying things out. I load ParaView 5.10.1, that's important here, the one. And then I copy my catalyst script. I copy my ParaView catalyst Python script to my running directory, and I pass it as an option to the running simulation. And then the rest of the options are for the code itself. Let's look at the content of this PV catalyst. Now, how many people here in the room use ParaView daily or once a week or once a month? You've used it at least once. All of you die. Yes? So you've all seen a ParaView Python script. What does it have? It has this, from paraview.simple import star, right, etc., etc. Get material library, create a view. This is standard ParaView. We've all seen it. Well, that's the script that we're going to use for the in-situ coupling. And I'll stop here for the moment. I will not show you the rest of the file. How do we run and specify the content of this script? That's the question. Hello. There we go. So, since version 5.9, ParaView has the so-called extractors, and I'm going to give you a live demonstration of that. With extractors, you can save data, you can save images, you can save any data at anywhere in the pipeline of your visualization. You can save data. Just like earlier with Ascent, we would specify the name of a pipeline to say, I want to use the relay to save that part, for example, the isosurface to file instead of saving the grid to file. Here, it's the same with the data extractors. We select the current object we want in the pipeline, and then we create an extractors associated with it. And then we have the image extractors. Using the extractors means that in most of the cases, at least at the beginning, you will not have to write any custom code. A few slides earlier, I said that the Catalyst API had 5 calls: initialize, execute, finalize. What the heck do you put in there? The answer is nothing at the moment. It's there, it just works by magic. I love it. So, using extractors, in most cases, it's going to just work. If you want to customize things, then you will fill up this catalyst execute phase with standard Python code. So it's not so much more difficult. The Python script which we will use will be derived from a live, from a running session of ParaView. You can be connected to a remote server if you want, but you can also do it with a small data set locally. You will add the extractors, and everything, the whole parallelism that is under the hood in ParaView, MPI enabled, TBB, CUDA, all those things will be packaged in, and you will benefit from that in situ if you select the appropriate filter. All right, so I'm going to load a Lulesh data set, and I want to color the data by velocity. Those are basically the five lines of code I need. Grid, open data file. This is the name of my file on disk. Okay, so this is not in situ. This is a copy of a small data set that you have run with a small scale version of your simulation. You save that to disk, you load it. You do everything you want with your visualization app. You open the file, you create a view, you show it, you color it by velocity. And when you save the Python script, what is new in the most recent versions of ParaView is that it adds those 2 lines of code from paraview.simple import save extract using catalyst options. We will see what those options are. This is the code to run ParaView in 2 modes actually. In batch mode, so I could reload data from disk on Pete's date and have it save an image, or I could use my desktop application, run it, connect to the server, and load this script. Fine. Here on the right is the version of the code we need for in situ. It's not blank, it's actually almost exactly the same content. Actually, those 4 lines here, they didn't fit on the screen. Otherwise, it would be the same. The only line, this is 1 line that has changed, is this. Instead of reading the data from the disk, I read it. This is a kind of a hack, kind of a black box. It's a replacement to say my data comes from the simulation. The key point here is that this particular string called grid is what appears in the conduit mesh definition. Your data is actually called grid. Well, in this implementation, you can call it whatever you want. Just make sure you use exactly the same name as you've used in your conduit mesh definition. Everything else, I swear, is the same. Those extractors didn't fit on the left page, that's the only difference. So this is what the Python code looks like. If I save my grid to disk, ParaView gives me the option of a trigger. Well, in this case, there's no other option than triggering on the time step. So that's what it is. And I select here a frequency of 30. It's up to you. And I give it a file name, and I'm done with that. I've mentioned those calls, those 3 calls. Finalize, I usually do nothing, I just close. Initialize is where I pass the name of the script and some other options. And execute is something, if I want to do something special. So I have an example a bit further. I'll show it to you. Code instrumentations, again with the SPH-exa solver. At the time I did the exercise, this was 140 lines of code. So really, really pretty trivial. This is your code in most cases, no? You do an MPI init, initialize your code, whatever it is, and then for a number of iterations you solve for a given time step. And then you exit, you close MPI, you exit. For in-situ, you add the catalyst initialize call. At each time step, you execute, but it doesn't mean that you actually do. You're not obligated to do some work. If inside your Python script, you're saying, at a frequency of 100, every 100 time step, save the data. The rest of the time, this is a no-op call. You go, there's nothing to do, you go right back. There is an example of a customization of the catalyst execute command. Always for the SPH-exa script simulation, I wanted to threshold, I wanted to select the particles with a density greater than 1.4. This was, at the time, what looked good in the picture. So there's the code. I set my threshold. From my reader object, let's not be confused, this is just a name, this is a placeholder, it doesn't read data from disk, it's just the name of the object. It's the conduit node definition. If the density stored as a point data, maximum value, that's the second number, is greater than this threshold, extract those particles. I didn't show you the code, but it's a couple more lines of Python. Otherwise, use all particles. And this, in my simulation box, I don't know if you see it, but here I removed those particles on the 8 corners of the box where the density was smaller. So this would be an example. So this is actually very, very similar to the classic Python script which the application gives you. All right. I will stop here. I will give you a live demonstration of ParaView. There are questions? No. Just to save on time, if I remember where the data is, I will run ParaView locally on my desktop. Okay, there's my data. All fields, variable here available. I can select which ones to load. I will just load them all. It's pretty small data. It's only 1 million particles. Yes, it's 1 million. There's my data. I can color with density. Okay, pretty much with there. You can see it already when I go to low resolution. All right. I could select with my threshold. But I'm going to do something even fancier. I'm going to switch representation to something called the point Gaussian. And the point Gaussian has the ability to scale the representations of the particles by a scalar field. And I'm going to say, if I find it, eccolo qua, use scale array. And there, by magic, actually, the low density particles have disappeared, because by default, it uses a linear ramp. So not only for the colors, but also for the size of the particles. But I can do more. I can edit this transfer function, and I can add, if you can see it, I can add some more particles, or I can remove some particles, etc. Bene. All right, I want to save this data to disk. I go here, I have a category here under Extractors, and I'm going to select Images, PNG, and by default it has created an extractor with a file name which is indexed by time step, which has a given resolution, it has a given frequency. Now I can say, I want to save every 33 time steps. I say apply. There, that's all we need for the demonstration. I'm going to save the state, and I'm going to call it state1.py. It defines an extract directory, which you can change if you want. And actually, I will do more than save state. I will say save catalyst state. I will overwrite this file name, this file, yes, because the interface is a little bit more. It also defines a place where to save the data. It defines global attributes, and here it has additional options for Catalyst Live and a Catalyst Live URL. This is to say, I want the simulation, when the simulation executes this particular Python script, I want it to enable a live connection, and I want it to listen to an incoming request for connection at this particular URL. And you will see the video of it. I save this and I quit, and I'll show you now the content of the file. Is it, how do I make this bigger? I don't know. Important is this. Here, is it readable from the back? What editor? How can I make the font bigger? I don't know. View. No. Well, that works in the browser, but here I don't think so. Oh, let's do it like that way. State 1. Let's do it that way. Yeah, sorry about that. This is my script. Create view. Okay, fine. Nothing interesting, nothing interesting. Here's my reader. I'm going to substitute this with this black box, this template, trivial producer it's called. And the registration name, here it used the name of the file which I loaded. But this is where you would put, for example, for simplicity, the registration name, you would put grid, and it would match the name you have in the conduit mesh definition. You do it once and then it will become automatic. In that case, there's no more the need for the selection of which variable to load, because now we're going to be connected to a simulation. The simulation via the conduit mesh will have made all its arrays available. And the rest of it is the same. I show my data. Until I get here. This is the new stuff. Set up the extractors. I have an extractor for images, so the format is PNG. It uses the given view. It has a frequency of 33, just like I had said, and then you can change that later on. It has a resolution, and ParaView will execute that image rendering at every 33 time steps. And that's it. If I had put an extractor for the data, it would also have an extractor for the data. Okay? So in the examples I have put for Lulish, I have several extractors which have been defined just for you to look at as an exercise. Just one more time so that you get it for good. You replace the call that opens the data from disk. You replace this with a trivial producer, and the registration name matches the conduit node definition.
What is the file format, VTPD?
What is the?
The file format you used, .vtu or
Okay, over here. Here the file extension is VTPD. It's an assembly, meaning a container of multiple file in the format XML VTP, which is a polydata. All those VTK and ParaView has a family of file formats based on XML. And there's one of them called VTI for image data, one of them for rectilinear data, one of them for curvilinear, one for polydata, one for unstructured, etc. And then the V, I forgot exactly the combination, but those are containers, quindi multiple polydata object here. And in the previous example I had, I guess we didn't have it. Okay, fine. Okay, operations controls. This was back from my introduction. How do we do this? Can we put the human in the loop? Yes, we can. So here's how we do it. I will open a port on a reverse tunnel to my desktop. So my desktop is here. I want to connect to Pete's Daint, which is over there. I SSH with this particular port number 22,222. That's the default port for the live Catalyst simulation connection. You can change that number. This is exactly what ParaView wrote at the bottom of my Python script. It wrote enable Catalyst live And then the URL, I gave it Daint 103, which is one of the logging node for PITS Daint, and I gave it the port 22,222. So I open a port to that logging node. My simulation is running already, waiting for an optional connection. I tell ParaView to connect, and then yeah, the 4 lines of code are here. Demonstrations, I'm not going to give a demonstration because it's a bit long, and I don't know if I have to wait for PITS Daint to give me an allocation. I will show you the video, which I have made as a screen capture. If I find the video. There we go. All right. First of all, I set up my reverse tunnel, so it's pretty small, but I go to PITS Daint, my job is waiting. I launch the ParaView client on my desktop. Over here, Catalyst, I do a connection to port number 22,000, etc. And I pause the simulation. There's a button here that went pretty quickly. Pause the simulation, get my data. This is the live data from the SPH exa simulation, and those are my particles for this particular simulation. At this point, anything available under the graphical, under the list of filters for visualization, I can do. So here's my threshold. I'm going to look here through the list, and I'm going to get another one, which is the SPH interpolator. This is a specific module to do resampling of SPH particle data sets. I'm going to resample the block here in this plane based on the smoothing length, the mass, and the density of the data. Once I have set up everything, the different thresholds, I apply, and ParaView on the other side, on the simulation side, will compute this plane interpolation across my cloud of particles. Here I put back my other data set. And in the meantime, the solver was stalled, waiting. So I have to give the control back to the simulation, and I can quit my simulation. Okay? This is the video playing again. Any question on this manipulation? I started the job goes on. The job executes my Python script. So if I told the job, the simulation job, to save one image every 33 time steps, it does it. I can still connect ParaView live. I stop the simulation. I grab the instantaneous data. I can apply to it any filters available, play with it. Of course, here I'm kind of sweating because I know I'm consuming my allocation budget. Well, I don't pay for at CSS. I work here. But all of you, you have an allocation budget. You don't want to say, oh, I'll just go to lunch and I'll think about it during lunch. No. Your job is consuming his budget. Yes, Sebastian. Question?
Could I, after I've stalled the simulation and decided that I want to look at this frame a bit longer, could I save that to disk
Yes.
and then resume the simulation, and then while it's running, look at that one image?
Yes. That's a good point, yes. All right, so we are pausing the simulation. We are connected live. We want to, before we connect, let's just elaborate a scenario. What do I want to look at? Okay, I know, I'm going for it. I connect, do my things, save images, save the current data set if I want, and then I release the control to the simulation, and then I can quit. Okay, there are other examples. Those are if you're curious. Examples of Lulesh, this simulation, build with the previous version of Catalyst. So it's VTK based. It means you would see the calls, the constructions of VTK objects. You can point to this place here and get the data, get the source code. Or the new version is the original version with Catalyst version 2, and then I have slightly modified that to enable either the Ascent compilation or the Catalyst compilation. So it's just a CMake flag with the same code. I can compile both. That's the main difference with the original code provided by Utkarsh at Kitware. All right, so now we have to decide which one do I like better. Do I like ParaView better? ParaView, the scene description would be this. This is straight Python. Create my view. There is the selection query from earlier. Select my point. The query string is density greater than 1.4. Extract selection. Display the selection. Create an extractor. Save an image at a given frequency. Or this is the Ascent version. You have a pipeline. This is still the old JSON version of the code, but I would now prefer the YAML version. Still, I define a threshold. I pseudo-color my particle based on pipeline PL1 defined above. I render my images. The other difference is that for Ascent, you do everything with conduit node definitions, both the mesh description and the visualization pipeline. With ParaView, you define the mesh definition with conduit. The rest, perhaps that's an advantage if you are used to ParaView already, then those are completely automatic to you. I mean, I do those things 6 hours every day. So it's really automatic. I could do it almost eyes closed. That's the standard ParaView code. Third method, if you're still undecided, you could say, hey, how about using the ParaView Python code, but I tell Ascent to execute it. That actually works. It's documented, it works, there are examples. There is an example on the distributions I have prepared for you. Basically, you still use your conduit mesh definition respecting the convention of the blueprint. And then a ParaView plugin based on a Python algorithm class is able to construct the standard variations of all the different mesh types available in ParaView. For example, the regular grid, the rectilinear grid, the structured grid, the unstructured grid. And it creates on the fly those VTK objects using, of course, as much as possible shallow copies of the data arrays passed to me by the conduit mesh. This is how the scene definition looks like for Ascent now. The syntax is the same, add an extract, but this time it has a type Python, and as parameters you pass it a ParaView visualization script. All right, so you could try this also as well, and you'll see that is an interesting way to mix the two libraries. In summary, conduit, you would agree with me, is very intuitive, very easy to adopt. Everyone who has used a dictionary will immediately get the concept of associating keys and values and then building a hierarchy of keys and values describing data following a given set of conventions. The scaling that has been proved on very large simulation, very large data sets, so I am absolutely not afraid of going to large scale. However, we're going to use resources in a very tight manner. So what I'd like to do with a given simulation, sometimes in the next, this year, but in the next future, I'd like to really evaluate the impact in memory consumption, the impact in CPU, GPU transfer. What does the data do? Does it actually have to migrate from one memory space to another in some cases? I mean, shallow copies, okay, good, but in reality, it's not yet completely clear to me how memory can be reused directly on the GPU, for example, if your memory is resident on the GPU. Although both Ascent and Conduit have a CUDA interface as a backend, so they are in principle ready to operate directly with the data on the GPU. So this is what I plan to do next. And then there is, I think this is more practical work, visualization pipeline creation, tuning, reusability. I'm very keen on being able to share, reuse Python scripts from one simulation to the next. Another thing which is still not supported 100%, even in the current ParaView today, is the scripting via Python of more elaborate animation scripts. Animations based on triggers, moving the cameras to a particular path, etc., following, tracking objects with a camera. All those things can be done. It's easy to do with the graphical user interface. It's already more difficult to script via Python. I'd like to see it in situ to get a real feel for it. However, as I said in the coffee break to Giacomo, I've spent so many years writing plugins, writing interface, parallel interface. I became quite good at it. Writing parallel interface for ParaView because people would come in with a new format, a format that was not supported by ParaView. Well, okay, this is done. I've become quite proficient in parallel I/O as a bonus. But now with this conduit stuff, hey, I don't have to do this anymore. Conduit, relay, save, HJ5, bam. I save my data to this, and I can read it back, visit as a plugin for it, and it works. Jean-Guillaume in the back here was telling me, oh, it doesn't work for me. It's perhaps just a version number. On Pit's date, I have visit 3.22, and that supports the blueprint HDF5 file format. Okay, so we're done with this. We can read it back in parallel if necessary. So no more writing plugins. That's 11 years ago now. I wrote this slide in November, so this was 10. Now we're in 2022. 11 years ago when I presented libsim, already people were saying, hey, we are very tight in memory. We cannot afford to link in with more libraries, bring more stuff in memory. We can't afford that. So the one of the answers to that is in transit. Absolutely. There's some early, I've done some early test of that. I'm not ready to give a tutorial now, but next year we'll do it, I promise, okay? It's written, appointment next year, May 10th, 2023. You're in? Okay, good. I think that's the end of my presentation. Resources are here. So the first one is the repo, which you can clone on your laptop, everywhere, anywhere you want. This will stay for as long as I work on this topic, so I hope several years, minimum. The slides of today are there. They're also in the repo. I will possibly make a few adjustments in the next weeks. I will update the repo, and you just do a git pull to get the latest. There's the Sensei Ascent tutorial, which is interesting if you want to explore also the Sensei venue. And then for anyone with a compute project at CSCS, I invite you to engage with me with discussion in the coming month. We say, okay, now this was great afternoon, but now let's do it. Let's do the code instrumentation with my code. I want to see it running in situ. And my gut feeling is that there's little, it's not going to be a revolution in your code. Your code is there ready with with its own structure. Conduit is both very flexible and both pretty simple, so it's not difficult to adapt or to integrate something simple in a big piece of code. If Conduit was a big machinery, it would take more effort, but here the effort, I believe, is minimal, so we should try it, okay? I have some multiple demos, toys, examples. There are examples in the four languages I've mentioned earlier. Now I'm becoming pretty serious with the SPH-EXA project, which will run at scale still in 2022, right? Yes, they say yes in the back. So we will run big cases in situ this year, and then I have another project already in the works of a large-scale simulation that is being instrumented with this. So the more experience I will get, and here now I'm talking about large-scale experience that can also apply to you. So I invite you to get back to me in the future. And please, this is the first time I teach this topic actually, because this is pretty new. Last year at Supercomputing in November, I believe was the first time Ascent and Conduit were presented, if not the second time. It's new. In any case, ParaView Catalyst version 2, this is new as of end of 2021, so this was only the natural progression for me to wait until this time, mid-2022, to be able to present things with a pretty good knowledge. Feel free to, in private, you all have my email, you can send me suggestions, criticism, whatever, help, contributions. I'll take it. Okay? Good. Thanks. Thanks a lot. Thanks a lot. Thank you. Thank you. Will, yes, now we can have more questions, yes.
So this is a non-visualization related question, and it's probably extremely naive, but it looks to me like, well, in our field, we've spent person decades or maybe even person millennia on couplers, right? Coupling one application to another. Ocean model with an atmospheric model, and then with a sea ice model, et cetera, et cetera. So I get the impression from these tools, Conduit plus Catalyst, that they're completely capable couplers between two arbitrary applications. Or that's an impression, or would you say that one of the applications has to be visualization?
No. My colleague Cyrus, colleague and friend, I mean, I've known Cyrus for many years. He's not going to tell me lies. Lawrence Livermore is investing a lot more on Conduit for the purpose of code coupling in general. Visualization is just one example of it. So I think we should, I don't have specific examples in mind. I could ask Cyrus for references of code coupling, multiphysics, the examples you've given, ocean code, atmospheric code, etc. Somebody must have already presented their results, their work, their feedback on that.
And so designed for performance, they have to be.
Yeah. In fact, in the Ascent documentation, there are examples. Yeah, there's a mini demo examples of code coupling. You can, I will help you look for the example. I will test it myself. There's two codes to compile, and they talk to each other.
Flo knows more about this than I do.
Well, does Conduit do remaps? Because, I mean, if you look at the climate model coupling, the nasty part is that the grids don't align, and you have to do various forms of remaps.
Yes, yes.
Sometimes you have to do conservative remapping.
Yeah.
So plotting doesn't disappear. I don't know if Conduit can do things like that.
On the top of my head, no. I mean,
From the visualization side, what happens is when you publish a mesh of some kind, you say, oh, X, Y, Z are in these arrays and whatnot. If the arrays on this side don't match the arrays on that side, then you can use a kind of an
Yeah.
I mean, they would put stuff like that in, so you could either, on demand, say, resample it onto the grid that I'm expecting, or interpolate using the sort of, lookup. And that's all.
Yeah, by remapping, you actually meant resampling. Is that
Not resampling, but
similar?
remapping the indices from X, Y, Z to
Yeah.
X, stride,
Yeah.
Y, stride.
They were both distributed, right? Both, some sort of domain decoding.
There is some nastiness in the whole game.
I'm sure.
With like like a field that only exists on the ocean grid, and then you want to. So there's a lot of nastiness in the details when you're working with the climate data, because you have like sea ice which lives on the ocean grid, and an ocean grid cell doesn't necessarily align with an atmospheric grid cell, so you might be mapping you might be mapping to an atmospheric grid cell which sees like a bit of sea ice, a bit of ocean, and a bit of land, which is basically missing value because it's not part of the grid. And you have to decide which properties you want to conserve in these remaps. So there's a lot of nasty details, and I think so. There's good reasons why we have a guy who's spending his time doing the coupler, and then the really nasty part actually comes when you have to bring the whole story back into the physics and anchor it so the physics does the right things with the fields it's getting. And there's a lot of kind of try and error it is in the end, because you're always violating some physical concepts when you're doing things with fields that don't really align.
Yeah, good point. I mean, pretty critical point. Time will tell with experience. Thanks. Any other comments? I know it's maybe a lot of stuff. Please take that home, digest it, and then come back to me. Okay? Yeah? Yeah, please, good, thanks. Thank you all for coming anyway. I didn't expect too many people. I'm glad to see interest. This is great.